So Gibbs free energy is named for Willard Gibbs, or I think he has a different first name. That's what he went by. And he wrote his first two papers on thermodynamics in 73 and 74. Okay? And he had a couple important assumptions for his term Gibbs free energy. Okay? But the good news is they're very biologically relevant for us. The first one is constant pressure. Okay? So Gibbs free energy is for isobaric or constant pressure systems, such as for us, atmospheric pressure for all of our biosystems. And additionally, constant temp, okay? Isothermal. The way we thought about this before, I said, the body was essentially isothermal. We have some regulation to keep everything at roughly body temp, so treat ourselves as isothermal. Another way to think about it, the surroundings are so much larger than the system that we think of temp being sort of maintained constant, which is another possible way. The notation for Gibbs free energy is a capital G, and the equation for Gibbs is enthalpy H minus temperature T times entropy S. This gives a state function. Why not? If you're saying no, why are you saying no? What is the definition of a state function? I can measure it at a given point in time. I can take it between 2 points. I've already written it like this before. I'll write it like this again. The fact that delta G is a thing means this is a state function. It's made up of all state variables. Enthalpy was a state function made up of other state variables, U, P, and V. Okay? T is a state function, and entropy, right? If you could calculate and a multiplicity of everything, like you could get a perfect measure of entropy of any given system, it's just hard to do. Okay? It's possible. And the other thing Gibbs said was that for a system that is at constant pressure and temp, Gibbs free energy will always decrease for a spontaneous process. Okay? The direction of spontaneity is to decrease Gibbs free energy. So here we have a plot. Gibbs free energy is on our y-axis, and we have our equilibrium point is a minimum. Okay? When Gibbs free energy is minimized, we're at equilibrium. Now change in Gibbs free energy with respect to this point is equal to 0, because again, we're at a minimum, so slope is 0. Okay? So we expect G to be minimized when we're at equilibrium, and dG, the change in free energy at equilibrium, to be 0. This is obviously also 0, okay? But this is clearly an unstable point where things would want to roll off of it down to some minimum free energy. The other thing to maybe keep in mind is, the Gibbs free energy curve, it's not just a U, or it could look very different. What is a local minimum versus a global minimum? Like a system could be at equilibrium at sort of like a local minimum, but it's not at its global minimum. But to get out of that state, you would have to put in some energy to get over the hump and get out of it, right? So there can be some, like I said, local minimum where Gibbs free energy is minimized in that area. There's a weird example that I have since cut about popcorn, about like the closed kernel was at like a local minimum, and then once you popped it and it was open, like we're back at a new equilibrium, but entropy went up, so it's like the global popcorn minimum. I don't think it went over well, so I cut it from the slides. People didn't like it. Okay, so again, if dG is 0 for you, then you are likely at an equilibrium point, unless you're maybe at an unstable point. And when dG is negative, okay, the slope is negative, this is the direction of spontaneous change. When the slope is positive, this is an inflection point, then you would have the opposite direction, the non-spontaneous direction. Okay, so here's the Gibbs equation. Here's the differential form, okay? And I'm applying my differential form to both T and S separately. So I have T ds minus S dt. This term drops out because we said Gibbs is only relevant for isothermal, okay? We only care about isothermal, so dt is not changing. I only go through this just in case I didn't think I needed to do this earlier and maybe people were not sure how I was getting to these capital deltas, okay? I'm integrating over each term separately, all right? So if I integrate with respect to dg, and I integrate with respect to enthalpy, and then I integrate with respect to entropy, okay? There is, no variable here, there is no function, they're all just nothing, okay? So it becomes g between final minus initial. It becomes an h between final minus initial. Temp is constant. I pulled it out in front of the integral. And then again, s final minus s initial. This is how I was going back and forth between like this version of equations and this version, in case anyone was struggling with that. I hoped people weren't meditating, okay? So we have Gibbs free energy. It's a state function. I can calculate it at a given point in time. What I really care about always pretty much in this class is change in free energy, okay, delta G. And the reason that's coming is because this is really hard to measure. Absolute anything is hard to measure. Almost everything in science is just relative to some standard that we set because we don't have a choice. Even PCR, for example, we have some housekeeping gene, some control gene, and we look at relative to that what is happening because absolute values are just too hard to measure reliably in most science. When delta G is less than 0, we have a spontaneous change. We call this a release of free energy, and what's this? Then the sign is negative, right? Energy coming out is negative. So that's our sign convention. Okay. Delta G, this release of free energy is the amount of energy that is available or free to do some kind of work with, okay? So the reason we care about this is that we can capture that energy that gets released, typically from some sort of chemical reaction, for example, like ATP hydrolysis. We get some energy out and then we use it to do something else. We couple it to some other unfavorable mechanism in the body and we use that to be the driving force. Okay. When we talk about work, are we talking about pressure volume work anymore? Probably not, because the body is isobaric and isometric for the most part, okay? We're talking about some of this other stuff that we could do, okay? So we could use the free energy we get from some reactions such as ATP hydrolysis to do mechanical work in muscle contraction, to again like drive the concentration change, concentrate a whole bunch of molecules inside a cell. Eventually it wouldn't want to keep going in and we can push them in with that energy. We can push things against an ion gradient. We could use a chemical reaction to produce light energy, whatever it might be.